Hi students, I am Mahesh. I am here to teach you 10th class mathematics. So in this class, the first main chapter is real numbers. So from this chapter, the learning objectives are fundamental theorem of arithmetic, Euclid division lemma, prime factorization, the finding of LCM and HCF, irrationality, logarithms. By the end of this chapter, we can get the knowledge about this fundamental theorem of arithmetic, Euclid's division lemma, prime factorization for finding of LCM and HCF, irrationality and logarithms. Real numbers. What are real numbers? The definition of real numbers is the combination of rational numbers and irrational numbers is called as real numbers. In previous class of basics already we have learned what are rational numbers and what are real numbers, irrational numbers. We will discuss again one more here. Rational numbers and irrational numbers. Rational numbers. The numbers which can be written in the form of p by q, where p comma q are integers and q is not equals to 0. So let us take definition here. The numbers in the form of p by q, where p comma q are integers and q is not equals to 0. Here p comma q are integers. P and q, whatever it may be that integer, but q should not be equals to 0. Q is here playing a role of denominator. That means if the denominator is 0, we cannot divide in a proper way. So that's why the q should not be equals to 0. Now, irrational numbers. The definition is the numbers which cannot be written in the form of p by q. That is not equals to p by q, where p comma q are integers and q is not equals to 0. For this irrational numbers, example is root 2, root 3, root 5 and so on. Not only like that, the 1.7325685 and so on. See, if you observe this one in decimal portion, it is not ending. And continuously you are getting some other digits. That means it is 7, 3, 2, 5, 6. Any other digit also it is not repeating. So these type of numbers are also called as irrational numbers. An overview diagram for this real numbers. See here. It is a natural number and whole numbers, and it is integers and rational numbers. And these are irrational numbers. And the combination of these two types of numbers is called as real numbers. See, here it is completely rational numbers. In that only integers are it's contained, and whole numbers and natural numbers. That means any subset to whole numbers. The set of natural numbers is subset to whole numbers. And this whole number also is subset to integers, and the whole numbers, that means natural, whole numbers and integers, all are subset to rational numbers. Now, irrational numbers is different. Now, the combination of this rational and irrational, that means rational numbers and irrational numbers, combination is called as real numbers. This is also called as a Venn diagram related to in the way of sets. So in the process of learning of this chapter, the first main concept is fundamental theorem of arithmetic. First concept is fundamental theorem of arithmetic. What is the meaning of fundamental theorem of arithmetic? So, in number system, for any number we can write factors. That means, for example, 2, 3, 5, 6, 7. These are all numbers, and for 2, 1 is a factor, 2 is a factor. And for 3, 1 is a factor, 3 is a factor. And for 6, 1 is a factor, 2, 3, 6. These are the factors for 6. That means this number, in which table we are getting, those numbers are factors. Here, for this 2, we got only 1 and 2 factors. That means 1 and itself are the factors. Those numbers are called prime numbers. If the numbers has more than 2 factors, that means 1 and itself. For the 6, 1 and 6, the 2 are factors, and other than these 2, 1 and itself, other 2 factors are also there. That means if a number having more than 2 factors, those numbers are called composite numbers. Now comes to composite numbers topic here. If any of the composite number can be written in the product of 2 or more prime factors. Here 6 we are taking. So 6 we can write 2 into 3. 2 into 3. So 1 is a factor for every number. Now if you observe for this 6, prime factorization is 1 into 2 into 3. That means it has more than 2 factors. 6 is a composite number. Now for every composite number can be written as a product of 2 or more prime factors. This theory is called as fundamental theorem of arithmetic. And you can apply, that means applications of this fundamental theorem, where we can apply, why you are using, why it is introduced in mathematics. So for this ideology, we are using 2 applications mainly. That is, one is for the given rational number is terminating or not terminating, we can identify easily. And second is irrationality. If the given number is rational or irrational. If it is irrational, how it is irrational? We can get by a proof. And these 2 main theorems we can prove by using this fundamental theorem of arithmetic. And in next class, how the proofs will be calculated. We'll continue. Dear children, I think everyone is following our class. So the first chapter is here, real numbers. Last day we have discussed about the introduction of real numbers and fundamental theorem of arithmetic. So in this process of learning, our next concept is here Euclid division lemma. Euclid's division lemma. This one is called as by another name also. That is Euclid division algorithm. Euclid's, we have already heard this name. Division, yes, we know the division process very well. And what is lemma? Just we are listening this word in this class only. And algorithm, already we heard this word in previous classes. Now let me know about lemma and what is algorithm. Algorithm is a process that containing steps. When you are solving some mathematical problems, you are using some steps. That means using steps to solving a problem is nothing but algorithm. So once again I am repeating. Using steps to solving some problems is called algorithm. And what is lemma? Lemma is a proven statement. That means it's already proved, but that proven statement we are taking to prove another statement. Listen, a proven statement taking to prove another statement is called lemma. So how we are using this method in real numbers? If for example, I have 20 chocolates. 20 chocolates. I want to distribute these 20 chocolates to 5 children. So, how many I should give to each? How many chocolates I should give to the children? Equal. Let us take. First I am starting with one chocolate. 5 students. First person, second person, third person, fourth person and fifth person. Here 1, 1, 1, 1, 1. How many we are distributed? 5 we are distributed. Total how many are there? 20. So how many are left? Plus 15 chocolates are left. Now, so chocolates are left. I should give to each and every one. So now I am distributing 2 for everyone. 2, 2, 2, 2, 2. How many chocolates are distributed now here? 2 plus 2 plus 2 plus 2 plus 2. That is 5 twos. 10. 5 twos 10. How many are left? 10 left. Next. So many chocolates are left. Now I want to distribute 3 chocolates. 3, 3, 3, 3, 3. That is 5 threes. 5 threes are 15. How many are left? 5 chocolates are left. Now, again few chocolates are left. Now I am distributing 4 to each person. 4, 4, 4, 4, 4. So 4 5s, 20. No chocolates are left. So we are using some steps. Here, first step, second step, third step. By trial and error method, we are solving this problem. Now, no chocolates are left. Now, how many chocolates I can distribute for each person? Yes, 4 chocolates I can distribute. This you should applicable to Euclid division lemma. How we are taking total? How many persons are here? 5. That is 5 into 1. 5 into 1 plus how many chocolates are left? 15. For 5 persons, I am distributing 1 chocolates. 15 chocolates are left. Total how many chocolates? 20. So left. Next, these 20 chocolates I am distributing to 5 children. For each member 2. So 5 twos are 10. When you are taking 2 chocolates, how many chocolates are left? 10 chocolates. Now 20. I am distributing 3. That is 5 3s are 15 plus here 5. Here in third step 5 chocolates are left. Now 20, that is 5 into 4 plus 5 4s are 20. No chocolates are left. So how many chocolates I can distribute to each children? 4. So in this process, so that means from 6th class, 7th class already you have learned. If for example I have 20 chocolates, I should distribute to 5 children. For each student, how many I can distribute? So that means 20 by 5. You are dividing with 5. That means 5 ones are 5 4s. That means you can take like this division method. Divide with 5. 5 4s are 20. Remainder you are getting 0. 20 is dividend, 5 is divisor, 4 is quotient and 0 is remainder. And we are already well known about this division process. So why we are not taking 5 3s are here? 5 3s are 15. Why we are not taking So the number should be nearest to 20 or less by 20 or exactly 20. So 5 fours are 20. It is very near. That means equal to the 20. So we should take 5 fours are 20. We got remainder 0. That means this step is wrong. This step is wrong. This step is wrong. So this step is correct. So this is the process to apply Euclid division lemma. That means each and everything. First we should focus on this divisor and remainder. So now enter into the concept that always that remainder is 0 or more than by 0. It should be 0 or more than by 0, but it should be less than by the divisor. It should be less than by the divisor. If A is a dividend, B is a divisor. Now divide that A with B. So when you are dividing a number with another number, you will get a quotient and you will get a remainder. So just now we have discussed this problem. 20 you are dividing with 5. 5 fours are 20, you got remainder 0. 4 is a quotient, 0 is a remainder. Now this 20, that means this 20 we are distributing to 5 children. For each 4 chocolates we are distributing. And remainder you got 0. That is 5 into 4 plus 0. This 20 is equals to 5 into 4 plus 0. This is the process to apply Euclid division lemma. Now here apply for this here also. That is dividend is A. That is A is equals to B into Q. B into Q plus R. Where what you are observing here? This remainder is always is equals to 0 or more than by 0. But it should be less than by the divisor. So how you can give condition here for that? Where A comma B are real numbers and where 0 is less than or equals to or less than by B. That means this remainder should be less than by the divisor and maybe it is equals to 0. Remainder sometimes you will get 0 also, but it should be equals to 0 or more than by the 0. And this is the statement of Euclid division lemma. Once again I am repeating. A is a dividend, B is a divisor. Then A is equals to, that means dividend is equals to divisor into quotient plus remainder. What we can call this statement? Dividend is equals to divisor into quotient plus remainder. What we can call this statement? We are already learning in your previous classes. That is division algorithm. Same process we are taking. We are applying for Euclid division lemma. That's why we can call this Euclid division lemma also division algorithm. That's why we are used the name here. Okay, my dears. Now we take one example problem how to apply Euclid division lemma for these values. A is equals to 13, B is equals to 3. Where A is a dividend, B is a divisor. We'll go by stepwise steps. That is 13 is equals to, that means dividend is equals to divisor into plus quotient plus remainder. That is 3 into, first start with 1. 3 ones are 3 plus 3 ones are 3 plus how much is left? 10. So for applying this very well, you take divisions. 13 divided with 3. 3 ones are 3. You are getting remainder 10. 3 into 1 plus 10. What it should be? Remainder is always less than by the divisor. What is divisor here? 3. What is remainder here? 10. Is it correct? No. This step is wrong. Go for next. 13 is equals to 3 into. Now 13. 3 twos are 6. You are getting remainder 7. That is 3 into 2. 3 into 2 plus 7. 3 into 2 plus 7. Is this correct? No. Divisor is less by the remainder. So wrong. Next. Third step. That is 3 into. Now divide it. 3. 3 threes are 9. You are getting remainder 4. Is this correct? The remainder is greater, right? So this step also wrong. But apply here. 3 into 3 plus 4. This step is also wrong. Now go with 4 table. 3 fours are 12. Is this condition following here? Yes. Divisor is greater than the remainder. That is 3 into 4. 13 is equals to 3 into 4 plus what is remainder? You got 1. So when you are comparing these two values here, remainder is 1, divisor is 3. Yes, this following by this condition, and the correct solution is here, this one. For a is equal to 13 and b is equal to 3. So when you are applying Euclid division lemma, which step is correct now? 13 is equal to 3 into 4 plus 1. This is the required solution. Okay students, next, how to apply this Euclid division lemma into our mathematics. Now here, finding HCF by using Euclid division lemma. 50 and 70. These are the two numbers. For these two numbers, we need to find HCF. Now, HCF. What is the process we know already for finding of HCF? Yes, long division method. Long division method. So, which is greater number in that? Both 70. That you take in middle. Now, 50. 50 ones are 50. You got remainder 20. Next, this 50 you drop here. Next, 22s are 40. Remainder is 10. And this 20 drop here. 10 twos are 20. You got remainder 0. Now, this 10 is HCF. HCF is equals to 10. But this is long division method. Already we are done in our previous classes. Now here, in Euclid division lemma, step by step, follow these steps here. First, this is the first step. 70 is equals to 50 into 1 plus 20. 50 into 1 plus 20. Now, we are taking this 50 and this 20. 50 is divisor, 20 is remainder. We should focus on these two only. That is what? Divisor and remainder. So 50 drop here and 20 drop here. Take is equal to here. So second step. Now go with second step. That is 20 into 2 plus 10. 20 into 2 plus 10. Now this is divisor, this is remainder. Next, follow 20 is equals to this 10. Now third step, 10 into 2 plus 0. 10 into 2 plus 0. See, finally we got remainder 0. Now drop this one here, 10. So nothing is here for dropping. Why? Because we got 0 here. So how much we got now here? 10. This 10 is the required HCF. So required HCF of 50 and 70 is how much we got? 10. And And children, enough for today, and you work out on this problem. That is page number 3. Do this. Second, third, fourth. First one I have already done for you. Next here. Page number 4. Do this. Second, third, fourth. And first one I already done here for you. So same process you apply for that problems also. Enjoy it. Hi students. Lastly we have discussed about the statement of Euclid division lemma. We'll take some examples of Euclid division lemma. That means applications. Here, this is one of the example problem from our textbook, page number 5. Show that every positive even integer is of the form 2q, and every positive odd integer is of the form 2q plus 1, where q is some integer. First we take for even integers. Statement EDL, that is Euclid division lemma. Statement is A is equals to BQ plus R, where A comma B are real numbers and 0 is less than or equals to R is less than 1. This is the statement. Here, the even integer is of the form 2. So in previous classes we have already learned about even numbers, odd numbers. Even numbers. What are even numbers? The numbers which are divisible by 2 exactly are called even numbers. And what about odd numbers? When you are dividing the number with 2, you will get a remainder 1. Are called odd numbers. Now here, the same situation also will come in this problem. Here, A is a dividend. That means A is equals to, here, even integer. Even integer means it should be multiplied by 2. That means it should be divisible by 2. That means divisor is 2. And Q. What we should get? Reminder, when you are dividing with 2, you should get remainder 0. Right? If it is divisible by 2 exactly, that means if you are getting 0 remainder, that is even integer. That means A is equals to 2q. Yes, we need to prove that it should be in the form of 2q. Yes, we got. Next. This is for even integer. Next. For odd, A is equals to, when you are dividing with 2, what you should get remainder? 1. If you get 1, that is odd integer. Odd integer. And one more here, from these two concepts. If divisor is 2, what are the possible values for remainder? Remainder should be always less than by the divisor. What is divisor here? 2 is a divisor. And what should be the remainder? 0 and 1. Only these two possibilities are there for remainder. Why? Because 2 is the divisor. Okay? And less values for the 2 are 0 and 1. Now, here we got remainder 0. If you got remainder 0, that is even. If you got remainder 1, that is odd. Yes, for even integer is of the form 2q, and for odd integer it is the form of 2q plus 1. So here is second example. Read that question once. Show that any positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integer. Now, is of the form 4q plus 1, 4q plus 1. Now, write Euclid division lemma statement first. EDL. Here is solution. Euclid division lemma statement is A is equals to BQ plus R. A comma B are real numbers and 0 is less than or equals to R is less than by B. Always the remainder is less than by the divisor. Now here, compare this one with the given forms. A, what is A? Any positive or integer. A is any positive or integer. Next, B. Compare with the forms. What is B? Here, before that quotient is B. Here, that is 4. Now, Q is some integer, any of the integer. Some integer. Next, R. What is R? Here, it will depends on the divisor. What are the possible values for remainder here? Remainder should be less than by the divisor. Divisor is 4. What are the less numbers for that 4? 0, 1, 2, 3. These are the possible values. Now, if dividend is 4q plus 0, first condition, maybe the remainder is 0. 4q plus 0 means 4q. 4q, that means 2 into 2q. It is a multiple of 2q. It is a multiple of 2q. That means even number. That is even number. That means 4q is an even number. But what we need to prove? Odd integer is of the form of 4q plus 1. 4q plus 0 is not there in that. So, no need to take this. Next, if A is equal to 4q plus 1 is equals to 4q, you can write 2 into 2q plus 1. So, when you are dividing with 2 plus 1, you are getting remainder 1. So, what is the definition of this? When you are dividing with any number with 2, if you are getting remainder 1 means those numbers are odd numbers. So, the numbers are 4q plus 1 is of the form for odd integers. Yes, A is odd integer. Now take third possibility. First we are taken with 0 remainder. Second we are taken 1 remainder. Now we take 2 as a remainder. If A is equal to 4q plus 2, that is 4q, 2 into 2q plus this 2 into 1. Take the 2 common here. 2q plus 1. Now it is completely the product with 2. It is a multiple of 2. There is no remainder is left here. No remainder is left means it got a remainder 0. Why we got this like? Listen carefully. It is a multiple of 2. You got a remainder 0. So that's why this 4q plus 2. A is not an odd number. That's why it is not here. Now take third possibility. So first we are taking remainder 0. That is not an odd integer. Next we are taken 1. Yes, we got 4q plus 1 is odd integer. Third we are taken remainder 2. No, it is not any odd integer. Next you take plus 3. If A is equal to 4q remainder 3. Now 4q 2 into 2q plus 3. Divide with 2. 2 ones are 2. It is 2 into 1 plus 1. 2 into 1 plus 1. Take these 2 common. If you take these 2 common, here 2q is left. plus. Now from this also if you take 2 common, this 1 is left, plus 1, right, as is. Now observe this one. 2 into something plus 1. That means if you are dividing this 4 cube plus 3 with 2, you are getting remainder 1. If you are getting remainder 1, those numbers are odd numbers. So 4a is here odd integer. So first one, no. Second one, yes. Third one, no. Fourth one is yes. Now the possible forms are 4 cube plus 1 and 4 cube plus 3. Start here. Okay students, here is exercise problems 1.1. in the first bit, first problem. Find HCF of 900 and 270 by using Euclid division lemma. Here is 900 and 270. 900 is bigger number, 270 is smaller number. So 900. First, roughly solve this problem by long division method. If you use this method, it is easy to solve by using Euclid division lemma. So 900 divide with 270. 270 one side is 270. 272 is 540 and 273 is 30, 37, 21, 326, 7, 8, 10. It is near to that. So 270 3 is 8, 10. If you subtract 0, 9 and next 270 drop here. In 90 table, when it will go 93 is 270. See, you got remainder 0. HCF is 90. Now let us apply this problem for Euclid division lemma. Dividend is equals, that is 900 is equals to 270 into 3. 270 into 3 plus, what is remainder you got? 9. Divisor, remainder. Now drop this 270 here and 92 here. Now this will become divisor and remainder. This 270 is equals to 90 into second step, that is 270 is equals to 90 into 3 plus 0. 90 into 3 plus 0. Now 90 here and this one drop here. So here it is 0, already you got remainder. That means 90 only you can drop here. This 90 is the solution. So required HCF of 900 and 270 is 90. Okay children, in first exercise, first bit, first problem we are done here. I have done for you. Next, in that first bit, first exercise, first bit, 2 more problems are there. Second one and third one. That you work out at home. Okay, children, are you done homework? Now, second one also you take homework as usual like example problem. So now, come to third problem. Read this question once. Use Euclid's division lemma to show that the square of any positive integer, is of the form 3p or 3p plus 1. Square of any positive integer. First we will discuss with some examples. Any positive integer means I am taking 5 square. 5 square is 25. 25 here. Now 3p and 3p plus 1. That means what will be the divisor? 3. Divide with 3. 3 table. 3 6 are 3 7 are, yes, 3 8 are 24, you are getting remainder 1. So 3 into 8 plus remainder 1. 3 into something plus 1. Yes, we got a second form. Now we'll prove. We'll take proof. Right? Euclidean lemma statement first. What is Euclidean lemma statement? A is equals to BQ plus R, where A comma B are real numbers and 0 is less than R equals to less than by B. Now 3P comma 3P plus 1. Compare this with Euclidean lemma statement. A is square of any positive integer. Next B, compare with that form. B is 3. Next Q, any integer. Now reminder. Yes, I think you got already. Listen. Remainder will be depends on the divisor. That means it is less of the divisor. So what are the less than numbers for the 3? 0, 1, 2. 0, 1, 2. Now here 0, 1, 2 are the possible reminders. First, take first one. A is equals to 3q plus 0 if remainder is 0. Now, what is A? Square of any positive integer. Take square on both sides for this. Square on both sides. That is A square 3q whole square is equals to 3q whole square means A square is equal to 3 square q square. That is A square is equals to 3 square. We can write 3 into 3 and q square, right, as it is. Now this A square is equals to 3 multiple 3 into something. 3 into here. What is that something here? 3q square. Let 3q square is equals to replace with p. Now in the place of the 3q square write p. Now A square is equals to 3p. If you take in the remainder 0, we got it is in the form of 3p. Next, second case. If A is equals to, now go with remainder 1. That is 3p plus 1. Again, square on both sides. That is A square 3p plus 1 whole square. For this square on both sides, that is A square here, 3p plus 1 whole square here. It is in the form of A plus B whole square. So A plus B whole square formula is what? A square plus 2AB plus B square. Now apply this formula here. That is A square is equals to 3p square, that is 3p whole square plus 2ab, 2 into 3p into 1 plus b square. What is the b here? 1 square is equals to 3p whole square, that is 3 square p square plus here we need to take 3 as a divisor here. So that's why write this 3 first. 3. If you write this 3 first, 2p 1 are left. 2 into p into 1, that is 2p plus 1 square means 1 here. Now take 3 common from here and here. Here 3 square is there. If you take 1 3 common, 3p square plus 2p is left and plus 1, right, as it is. Now observe this one here. This is 3 into whatever it may be. It is something. That is 3 into something plus 1 you got. That means let what is there in this bracket? What is that something? 3p square plus 2p. Take 1 q. So a square is becoming now 3q plus 1. Yes, we got the second form. Now, after finishing with remainder 1, now next possibility is 2. If a is equals to 3q plus 2. 2 is the remainder. Now, same, apply the procedure. Square on both sides. That is a square 3q plus 2 whole square. Again, it is in the form of a plus b whole square. Apply that formula here. That is 3q whole square plus 2 into 3q into 2 plus 2 square. Here 3 square q square, reveal the bracket, and here take the 3 first and remaining you write later 2 into q into 2, that is 4q plus here 2 square 4. Here 3 is there, here 3 is there is no 3 here. But if you observe this number 4 is a constant. In previous problem we got 1 square means 1. So the remainder, when you are dividing with 3, the remainder should be less than by the 3. But here you are getting 4. That is more than by 4. That's why this 4 also changing into Euclid division lemma step. That is 3 square q square plus 3 into 4q plus this 4. I am writing 3 into 1 plus 1. How we are applied that one? See here. 4 divided with 3. 3 ones are 3, you are getting remainder 1. That is 3 into 1 plus 1. Right. Now here 3 is there, here 3 is there, here 3 is there. Take out the common 3. 3q square plus, if you take this 3 here, 4q plus, here take out the 3, 1 is left. Here, plus 1 is left. Now 3 into something plus 1. 3 into something plus 1. That something now if you take p, that is 3q square plus 4q plus 1. If you take p, substitute that place 3 into p plus 1. 3 into this is total p plus 1. Now observe this. If you have taken remainder 2 also, you got in the form of 3p plus 1. Like that, if you take any of the positive integer for that square, it should be in the form of 3p and 3p plus 1. And these variables are just variables. That means it can change depends on the situation. That means like that, for example, here I was taken p and it is proved that 3q plus 1. It doesn't matter. And here that value is unique. It can change by the situation. And here 3q plus 1. Here it is 3p plus 1. And first one is 3p. But you should get only these two forms, no other forms. And this one proved.